Hello, this is Jeffrey Fox again, and we're going to do the third unit in this section on e-commerce and lifestyle informatics, covering recommender systems and related technologies, to just cover all the different types of things which use similar ideas to guide and persuade and people to do things in buying buying items, getting jobs, and so on. We are, of course, using clouds. We're running recommender systems collaboratively. We're processing big data, and we're solving problems in lifestyle informatics with our usual collage. In this part of this unit, we discussed item-based collaborative filtering. Remember in the previous unit, we discussed user-based collaborative filtering. There was also content-based approaches to recommender systems. We will not discuss, those are done in a much more straightforward fashion, and we will not discuss those here. So if we look at user-based versus item-based, there was some issue as to, just in terms of compute time, as to how much effort it takes to do this. When in the user-based approach, one of the difficulties is you have to do this in real time to actually be interesting, and you will find that effort is quite high. These methods all have to be done in memory, so they're real-time methods, and you need to find the neighbors and make prediction. And for a large commerce site, this just doesn't scale properly. And you have tens of millions of customers and millions of items. And so you have many more users than items. And so the user-based approach, finding users near a given user, is a computationally particularly intense idea. The model-based approaches include several ideas, including clustering, but also item-based collaborative filtering. And here you save some of that compute time by doing things offline. And you can find out which items are near each other independent of the user. So you can actually store that information. So that when along comes Alice, and you know Alice, say, has purchased a particular item, you know which items are near that item because you've already have calculated that. So that's an idea behind these model-based approaches. You take a method that allows you to do some things offline. Clustering is extremely similar to the collaborative filtering idea. You take the set of items and divide them into groups, so-called clusters. They're not actually distinct. They actually sort of touch each other, but they're regions of this vector space of items, which are just where any item in that cluster is almost by definition near the other items, and so you can say things in the same cluster are likely to be have similarities to for a given user. So if Alice likes an item in a cluster, she might like other items in that cluster. So let's give an example coming from this wonderful book, recommenderbook.net, on item-based collaborative filtering. So we have here our friend Alice, and she has purchased, as usual, items 1 through 4. And we want to find out. I want to look at all other items. Remember, items are the relative number of items, relatively small number, even if there is a long tail. We want to look at all other items and see which ones are near the one she likes, or at least near the one she's rated highly. Maybe she's not so keen on item 2. And of course, user 4 hates item 1. But we're not. User 4 is only, these users are only here not because we're going to find users near Alice. We're going to find items which are near. We're going to find. We're going to look at item 5 and find out if it has, based on its rankings here. Here we have the rankings of item 5. We want to know whether these rankings can suggest that item 5 is near one of the items that Alice has purchased, and then we might want to recommend it to Alice. So In this case here, it's going to be turn out to be items 1 and 4 are the ones that are relatively similar to item 5 based on these rankings. So we're going to use a method which is pretty similar to the Pearson correlation. We're going to, but we're now summing over in a totally different, if we think of this a matrix of item versus users, we're summing in the opposite direction in the matrix, horizontally instead of vertically. And we're going to sum here over users. Here we have the users. And we're going to sum over users who've ranked both A and B. So we're trying to find a similarity between two items, A and B. We sum over the users who've ranked both A and B. And so we have a ranking from a user for A and a ranking from a user for B. We take the same effectively scalar product divided by the length of the vector. And again, the only reason why this is not a normal formula and a normal cosine is that you only sum over the users who have rated both A and B. And so it's not a true cosine, because normally true cosine you have to sum over all users, but you can't do that because you only know the rankings for some of the users. And when it's a little frustrating. Maybe a user has ranked A very highly, but hasn't ranked B, so you can't use that user. We only can look at users who ranked A and B. And remember, we're doing this offline because all this data sitting on our disks, running in HBase and HDFS and things like that. And we're going to fetch this information and do this calculation to find the similarity, and then we're going to take each. If we look at this, A is going to be item 1 through item 4, and B is going to be item 5 in the previous slide. So given these similarities, we're only going to keep items that here we have an item P, which is going to be item 5. And we're going to look at the items which Alex has rated. Alice has rating, so I runs over items 1 to 4. We have the rating of U is Alice, U for items 1 through 4. I runs over 1 through 4 in this simple example, or generally it runs over all items that Alice has ranked. We weight with the similarity and divide by the sum of the similarities. And of course, we only sum over those items which we know have a high similarity. And we also explained in the previous unit how you might actually try to enhance those similarities near 1 by, well, I gave a random example of raising similarity to the 4th power. It can be the 8th power or the 2nd power or the 1.1 power, but all of that will enhance the items that are near the one we're trying to predict. And typically when you're in a big system, you really probably have a lot of items actually near a given item. And so you just choose a locality domain. So you choose from 20 to 50 neighbors, came from this 2002 paper. As I've mentioned, this field is a little frustrating. A lot of the references are very old because people have not, originally this all started off academically and there were lots of nice studies, but then it moved off into industry. And as this is a proprietary, incredibly valued to know how to do this exactly, that those industry will not tell you the value of K. They will not tell you how they enhance nearby similarities and things like that. That's all the secret sauce that just like the formula for Coca-Cola, that secret sauce is what makes that company succeed. And so here we have a basic summary of item-based collaborative filtering. You pre-compute all the calculable item-item similarities. And maybe you make a cut that only items which have a certain number of users in common can you calculate it. If 2 items only have 3 users in common, that may not be enough to make a reliable prediction. Then you take along comes a user. She logs in, and you know immediately what she's purchased or ranked in the past. And then you secretly, while she's drinking her coffee and deciding what to do, you immediately run your algorithm because you know she'll want to have some predictions, and you find the kth nearest neighbor based on the item similarities of each of Alice's items. So you actually have k neighbors, k times na items from this. You remove from that k times na items duplicates, ones that aren't actually available, already purchased by Alice, already so. And then you take this pruned list of items and order it using that prediction function we had on the previous slide. And so that's what you returned. And that's the so-called, that's what Amazon gives you when you search by relevance. Or when that's not just Amazon. When you search by relevance, you get something searched by this prediction, by this predictive ranking function.